Good evening, students, and welcome to today's session. Okay, so this is Newton's laws of motion, session number 10 for us. And today we will complete some selected questions from H.C. Verma exercise before we move on to the next section, which will be about friction. So we will do some examples from H.C. Verma exercise, the same chapter. So last time we had covered quite a few questions up to, I think, question number 21 or so, or 20 or so. Okay. So we will start with question number 21 today. Please go through question number 21 and I'll explain the meaning of the question to you. Okay, so this is a slightly different question in terms of the way the question is framed, because what is happening here is that instead of free body diagram or external forces given in that sense, okay, what is given in this particular question is that there is an external force acting on a body which depends on a certain vector relation. So it involves a cross product kind of relation. Yeah. So it involves a cross product sort of relation. So it says that there is a force given by the relation V cross A. Okay, this kind of force acts on a body when it is moving at a velocity V. Okay, where A is a constant vector in the horizontal plane. It's a constant horizontal vector. So now we have to find the minimum velocity with which it should be projected. Okay, what minimum speed this particle of mass m should be projected with, so that it continues to move undeflected with constant velocity. Okay. So this body is of mass m. So find the minimum speed of projection so that the body moves with, we can say, uniform velocity, because it's already saying that it should not deflect. That means the direction of velocity should not change, and its magnitude should also remain constant. So that means both magnitude and direction of velocity should remain constant, which means it should remain uniform. The velocity should be uniform. That means the acceleration of the body should be zero, which means the net force acting on the body should be zero. Now the net force here will consist of what? The net force will be the vector sum of this external force that is acting, this one, plus the weight of the body. So this should be zero. Okay. So that means we want that the external force that is acting should be minus of mg. Okay. So in other words, F should be equal to mg in magnitude, and it should be vertically upwards. It should act vertically upwards so that it balances mg. So you have to just find the condition for that. Okay, that this quantity v cross a, it should act in such a way that its direction is vertically upwards and its magnitude is equal to mg. Okay, so let's understand how we can make that happen. So just make a note up to this point here if you're writing this down. Okay, so let's understand how we can achieve this thing. That the magnitude of the force should be equal to mg and its direction should be vertically upwards. Okay, so for that, suppose this is a horizontal surface for us. This is a horizontal plane. So the vector A being in the horizontal, right? A is a constant horizontal vector. You can see this. That means the vector A we can denote, let's say, like this. It's lying in this horizontal plane. So on the body, when it's moving with a velocity v, I want that this force F that we're talking about should act like this. This force, which is v cross A, should act like this. Okay, so that it is able to balance the weight of the body. The weight is mg acting vertically downwards like this. Okay, so basically you know that v cross A should be upwards. So you'll realize that the velocity vector of the body will have to lie in the same horizontal plane, but somewhere like this at an angle theta, so that v cross A is pointing upwards. Okay, so v cross A, you can see, which is the force F, will point vertically up in this diagram. You can see, okay, from the cross product method, and the magnitude of this will become mod of v cross A, which will be va sine theta. Okay, so now I want that the magnitude of F should be equal to mg. So va sine theta should be equal to mg. So the magnitude of the velocity in general should be equal to mg upon a sine theta. So I can see that the minimum possible value will be mg upon a, but that will happen for sine theta to be 1. That means theta to be 90 degrees. So when this velocity vector is perpendicular to the capital A vector, that time the velocity will have minimum magnitude and mg will get balanced by force. So the acceleration of the body will become 0. So this becomes the answer. The minimum possible magnitude is mg by A, and it should be in such a direction that it's perpendicular to A and v cross A is pointing vertically upwards. So that is the condition. The condition is that v is v minimum if v is perpendicular to A in the horizontal plane, okay, such that v cross A is opposite to gravity, opposite to the acceleration due to gravity. Okay, so basically, if this is my vector A in the horizontal plane, my vector v in the horizontal plane will have to be something like this. Okay, so that their cross product, so that they are perpendicular to each other, and their cross product is like this. This is their cross product. Its magnitude is va, but its direction is upwards, and that balances mg. Okay. So this is a three-dimensional diagram. V and A are lying in this plane, in this horizontal plane. Okay, so this question is a little bit about the application of cross product, which is unusual in vectors. Okay, so hope this question is clear to all of you people. So next, I want you people to work out one question, especially if you haven't tried this particular question before. Question 25 in HC Verma. I'm just putting it up on the board, so you can go through it and try it yourself. So in question 25, you have two inclines like this. Such that it's forming a triangle such that this side is 3 meters, this side is 4 meters, and this side is 5 meters. Okay. And there's a pulley like this attached to the top here. And a string going around the pulley such that it connects to two blocks, both of 1 kg mass. Let's say this block A and this block B. They are both of mass 1 kg each. And all surfaces are frictionless. Both surfaces are frictionless. So I want you to calculate, take the value G as 10, okay, and calculate the acceleration of each block and the tension and normal reaction. So find acceleration of A and B, the two blocks. Okay. Then find the tension in the string and the normal reaction on each block. Very easy question. You should be able to work it out, each one of you. So try this out and send me the answers, please. Yeah, work out this question first, Iitanshu, then we'll come to question 23 and 26. Yes, that's correct. The acceleration will be 1 meter per second square, or g by 10. Okay. So the main thing in this question is that you have to understand that there is a 3, 4, 5 triangle. So this angle will be 90 degrees. Okay. And this angle will be 53 degrees. And this angle will be 37 degrees. Once you understand that, rest of the question is easy. Okay. Because then you can see that the components of weight will be like this. Okay. mg cos 53 and mg sin 53 and mg cos 37 and mg sin 37. Yes, very good. That's correct. Oh. Okay. So once you figured that out, the angles are like this. The rest is simple. Normal reaction on B, normal reaction on A, and uniform tension acting everywhere. So that's like this. Okay. Now you can see that this is on the steeper slope. A is on the steeper slope. So A will be sliding down and B will be sliding up. So your equations will become like this. For A, you'll have the equation mg sine 53 degrees minus T is equal to ma, or 4 by 5 mg minus T is equal to ma. And for the second one, you have T minus mg sine 37 is equal to ma, or T minus 3 by 5 mg is equal to ma. So you just add these two equations and you get 2 ma. Okay. So your acceleration becomes g by 10, or 1 meter per second square. Now once you get that, you can also find out the tension. Tension becomes, okay, so 4 by 5 into 10 minus 1. Because the acceleration is also 1 and the mass is also 1 meter per second square. So the tension becomes, how much is it now? 7 newtons. Okay. And finally, the normal reactions. Six newtons. Eight newtons. Okay. Okay, next we will discuss question number 23. So if you finished working on this, just go through the question. I explain how to work it out. So the main fact about the 25th question was that you had to quickly judge that this is a right angle triangle. This sort of triangle or whatever, this sort of triangle. This is a right angle triangle with this angle 53 degrees and this angle 27. Okay. Right, now let's come to 23rd question. So it's based on that Atwood machine diagram, which is part of the 22nd question. So first let's solve the acceleration of the system, then we'll talk about the question 23 itself. So you're having the standard Atwood machine with masses on either side given to us, and they are 300 grams and 600 grams. So M1 is 300 grams, or you can write that as 0.3 kg, and M2 is 600 grams or 0.6 kg. So we know that this one will be accelerating down, lighter one will be accelerating up. And when you solve the free body diagrams, you will get the acceleration like this: M2 minus M1 upon M1 plus M2. So in this case, you will get the acceleration as g by 3. So this part is actually question 22. So we already worked this out. Now in 23, what they're saying is that this system, it starts from rest at time t equal to 0, and at t equal to 2 seconds, okay, the block M2 is momentarily stopped. Just for an instant, you're stopping it. Somebody is like holding the block for an instant and releasing it. So released immediately. So when you stop the block M2, what will happen? The string will suddenly become loose. Okay, so at t equal to 2 seconds, the string will become loose. So to find after how much time the string becomes tight or taut. Again. Okay. So this is a question more about kinematics application actually. Let us understand this. Okay. Find the time before the string is tight again or taut again. Okay. So to understand this question, first of all, let's figure out what is happening between this time and this time, 0 and 2 seconds. Okay. So from t equal to 0 to t equal to 2 seconds, the system has an acceleration of g by 3, or you can write that as 10 by 3 meters per second square. It started with initial velocity 0, so the velocity will become at, or 2g by 3, or 20 by 3 meters per second. Okay, so let's just visualize this whole thing. So let's say initially the blocks were like this. Okay, at t equal to 0. So when you release them, immediately they develop some tension. Okay, and they develop this acceleration. So they started from rest. Okay, so this is what the system started from at t equal to 0. Now at t equal to 2 seconds, what is happening? By the time 2 seconds are gone, the heavier block M2 has come down a bit in comparison to this, and the lighter block M1 has gone up a bit in comparison. But not only that, this has now developed a downward velocity v, and this has developed an upward velocity v. Okay. And still the string is tight. Okay. And still they have the same acceleration g by 3 upwards and downwards. Okay, so this is the situation. So if I see just before stopping M2, stopping this block M2 at t equal to 2 seconds, the speed will be 2g by 3 or 20 by 3 meters per second, like this. Okay. Now what happens after you've just stopped this block? So what you're doing now is you're stopping this block momentarily and then releasing it immediately. So the moment you release it, now what happens? So now at this time, M2 is stopped, okay, and released immediately. So the moment you stop that block, the string suddenly becomes loose. No? Because why the string becomes loose? Is because on this side M1 is going up with that velocity, but M2 on the other side is being stopped. So its velocity has become 0. So the string loses its tension. The tension in the string becomes 0 just after M2 is released. This is what happens. So the tension becomes 0. So the moment the tension becomes 0, force acting on each block is just mg. So this also has a downward acceleration g. This also has a downward acceleration g. Okay. So what happens is that after this time, okay, so from t equal to 2 seconds onwards, okay, till the string tightens again. Okay. Both blocks have acceleration due to gravity. As their acceleration. Okay. They have an downward acceleration of g as their acceleration. So M1, it goes through like a vertical projection type of motion with an initial velocity of that v upwards, which we'd seen was 2g by 3 or 20 by 3 meters per second square. Okay, upwards, and an acceleration of g downwards. Whereas what about M2, the other one, it was stopped now, so it goes into free fall starting from rest. M2 is in free fall from t equal to 2 seconds onwards. Started from rest and it has an acceleration of g downwards. Okay. So use this fact now to try and find out that how much time it will take before the string becomes tight again. I'll explain it in a moment, but just try to use this fact. Okay, so try to visualize the situation and try to understand what I've written over here in terms of the motion after t equal to 2 seconds. When you stop this block M2 for a moment and release it. So the moment you stop it and release it, tension stops acting on it. So it goes down in a vertical free fall. You stopped it and released it. Now G is acting on it. No tension is acting on it. So it's in free fall starting from rest. Whereas the other block, it has an upward velocity and suddenly the tension has disappeared. So instead of continuing up with a velocity with an acceleration, now it is going up with that velocity v, but it's having an acceleration downwards because of its weight pulling it down. So it has a decelerated motion as it's going up. So immediately after t equal to 2 seconds, the block M2 will have an accelerated downward free fall motion, whereas the other block M1 will have a vertical projection and it will decelerate at the rate of g. Its initial velocity is 20 by 3 upwards, and because of gravity, it's decelerating at the rate of 10 meters per second. Okay, so now see, we want to analyze when the string will become tight again. So this is the situation just after M2 is released, now at t equal to 2 seconds. Now we'll compare this with a bit of time later. Okay. So this is the string, just about the string has become loose. This is at t equal to 2 seconds, just after M2 was stopped. And released. Okay. Now compare this diagram alongside a bit of time later. So by then what has happened is that this block has gone up by some displacement S1, okay, and this block has come down by some displacement S2. Okay, this block M1 and M2 are respectively having downward displacement and upward displacement, and let's say the time here is 2 seconds plus delta t. So in delta t time, what has happened? This displacement S1 will be V delta t minus half G delta t square. So that is 2 by 3 G delta t minus half G delta t square. This is S1, whereas this one is in free fall starting from rest. So this will just be half G delta t square. Okay. Now if the string is just becoming tight at this moment, okay, if the thread is about to tighten, it's about to get tight again at 2 plus delta t, what should happen? S1 should be equal to S2, because this is the point when the string started becoming loose. No? So from there, if this block goes up by a certain distance, but this comes down by the same distance, so again what will happen? The string will be ready to become tight again at that particular instant. Okay, so that is a condition we have to apply. No? So we have to just apply this condition now, that S1's value, which is 2G by 3 delta t minus half G delta t square, should be equal to half G delta t square. So you get this equation that 2G by 3 delta t should be equal to half plus half 1 into G delta t square. So delta t will come out to be 2 by 3 seconds. or 0.67 seconds. So the total time, of course, will be 2.67 seconds, but how much time later the string is becoming tight again, that will be 2/3 of a second or 0.67 seconds. Is the calculation clear, Hitansh? Okay, good. Okay, now Hitanshu, you also asked question 26. So I'll just give you the free body diagram for question 26. And I think you should be able to solve that yourself. And we will also do question 28. Okay, 28 is a bit of a tricky question. So I'll explain the method to you and we'll discuss that next. Okay, let's come to question 26. I think this one should be fairly easy. Anyway, let's go through it. So in this particular question, you have that very standard kind of situation, smooth horizontal table kind of thing. Okay, with a pulley attached at the corner. The only difference is we are pulling this block on top with some force. Okay. Yeah, I'll explain. So यहाँ पे देखो इसका मास m1 है, इसका मास m2 है, ठीक है, और मैं क्या कर रहा हूँ, I'm pulling this with a certain amount of force F. Okay. Now the thing is that see, I cannot be sure that whether the force I've applied is enough to make the block slip towards the left, m1, or it's going in the original direction, which is down towards the right, because we don't know which one will dominate. What is happening, iska jo weight hai, that is trying to make the system move like this, that this should go down and this should go like this, but then this force is trying to make it go in the opposite direction. So we don't know which one is dominating right now. So how we find out which one is dominating? We will just make an assumption of some direction of acceleration, and according to that assumption, if the direction of acceleration is fine, then we will get A with a positive sign. If the direction of acceleration is opposite, then we'll get A with a negative sign. You understanding it, Anshu? So मैं कुछ भी assume कर लूँगा that the acceleration is in a particular direction, and I'll solve the question with that assumption. Now, if the acceleration that I get comes out to be negative, that means my direction should be reverse, but the magnitude will still be the same, what we got. So basically the equations will take care of it. Okay. So I will just assume this direction of acceleration and write the FBD equations. No? So assuming acceleration like this, I have T minus F is equal to M1A, and I have for this one M2G minus T is equal to M2A. Now solve these two equations. Now on substituting the value of F, if I get A as positive, then the directions are fine. If I get A as negative, then actual direction is opposite. Okay, but the magnitude of the acceleration will still be the same. But the magnitude will come out to be correct. Okay, so that's how we solve the question. Okay, so try this out if you haven't done this, and next move on to question 27. Sorry, 28. Next we'll discuss question 28. So in 28, I will give you the hint that the upward acceleration of block M1 will be equal to the downward acceleration of the pulley, okay, attached to the thread by which M1 is attached. Okay, there's the pulley at the other end of the thread to which M1 is attached. So वो pulley का जो downward acceleration होगा वो उतना ही होगा जितना M1 का upward acceleration है. So take that into account and make the free body diagrams and solve for accelerations. Just try out this question now, we'll discuss. Yeah, Tanchu, your answer for 26 is correct. Now let's come to 28. As I said, it's a bit more tricky, this question. Okay, so let me explain how we'll make use of the hint that I've given you. Okay, so okay, just verify the answer in that case. Okay. Now what I was saying is that this pulley P2, both are massless. Okay, so P1 and P2 are massless pulleys. So as we are discussing, whenever you have a massless pulley, if the tension in this thread is T, then the tension in this other thread should become how much? It should become 2T. This should become 2T, because a massless object will have net force acting on it always equal to 0. So if this tension is T prime and these two tensions are T, but this is massless. So mass is 0. That means T prime minus 2T should be 0, because it's mass into acceleration. That's how we know that T prime is equal to 2T. That's the first thing. Okay. So we'll directly take this tension as 2T. Okay. Now secondly, if this particular block here is having an upward acceleration of A, then the pulley P2 will have the same downward acceleration A. Okay, so pulley P2 has acceleration A downwards because block M1 is having acceleration A upwards. Okay. And in the frame of this pulley, this is the lighter block M2 and M3 is a heavier block. So M3 will be coming down with an acceleration A3, but this is relative to the pulley P2. And this will be going up with an acceleration A prime, but that is also relative to the pulley P2. Okay, so this is what I meant by saying that we have to take this into account, that this. Okay. So what we'll do next is we'll make the FBDs of M1 in ground frame. Okay, but M2 and M3 in pulley P2's frame, and that will be a non-inertial frame which is coming down with an acceleration E. So we'll have to make use of the concept of non-inertial frame and pseudo force. Okay, so this is what we have to do here, and of course, given the masses are 1 kg, 2 kg, and 3 kg respectively, okay, so next up, make the free body diagrams and use them to calculate A and A prime. And from that, I'll tell you finally how we'll get the acceleration of M2 and M3 in the ground frame. Okay, we'll discuss about that also. But have you done this question, this 28th one? Okay, good. So I'll just give you a hint for 32. You can try it out in the meantime. I will be coming to that question. In 32, you have to use the constraint relation, no? Because there's system of pulleys. So if the block 2m is coming down with some velocity or acceleration, the block m, which is on the inclined plane, will be going up the inclined plane with double the acceleration or double the velocity. So that constraint relation has to be used. Just like in question 31 also, the constraint relation is there, like that in 32. So if you finished question 28 already, you can try out this question 32, even 31 and 32, you can try out with the constraint relation concept. Yeah, I'll get back to that after just finishing this one. Okay, so I'm moving on to make the free body diagrams now. So as I said, we'll make the FBD of the block M1 in the ground frame. So M1 in the inertial ground frame is going up with an acceleration of A, and the forces acting on it are T prime, which we've already written as 2T, and the weight M1G. So we have the equation 2T minus M1G is equal to M1A, okay, or 2T minus 10 is equal to A, because M1 was 1 kg and G I'm taking as 10 meters per second. So that's my equation 1. Whereas M2 and M3 I'll make in the non-inertial frame. Non-inertial frame of the pulley P2. So that non-inertial frame itself is coming down with an acceleration of A. And in this frame now, the block M2 is going up with A prime and M3 is coming down with A prime. So these are the acceleration. A prime is the acceleration of M2 or M3 with respect to the pulley P2. Okay, that is in the non-inertial frame of that pulley. Okay, so first of all, in that I have to show pseudo force. So pseudo force is M2A for this one, M3A for this one. Pseudo force is always opposite to acceleration. Okay. Pseudo force. Okay, and then the actual forces: tension, weight, tension, weight. Okay. So for the second block, I have the equation T plus pseudo force minus weight is equal to mass into acceleration. Okay. So this will become T plus 2A minus 20 is equal to 2A prime. So this is my equation number 2, which I've written for the second block. Okay. And finally, for the third block, I have the equation weight minus tension minus pseudo force is the net force downwards. That is equal to mass into acceleration. So I have 30 minus T minus 3A is equal to 3A prime. Okay. So this is becoming my third equation. Now I will solve these three equations for A and A prime. So what I can do is I can add second and third equation. Okay. That will get rid of T. So I'll have, now this was because M2 was 2 kg. And this was because M3 was 3 kg. So anyway, when I add these two equations, I'll have on this side 10 minus A, and on that side is 5A prime. So I'll have this relation that 5A prime plus A is equal to 10. Okay. And similarly, what I can do here is I can use equation 1 and 2. So if I do equation 1 and equation 3, so okay, plus 2 times equation 3, then again I'll get rid of T and I'll get another relation between A and A prime. Okay. So I'm adding twice of equation 3. So I have 30 into 260 minus 10. So that is 50. Okay, then T is getting cancelled, minus 6A. We have doubled this is equal to A from here plus twice of this. So A plus 6a prime. So I have one more relation, that 6a prime plus 7a is equal to 50. Okay. So now I can solve this equation and this equation, and from this I can find out a and a prime. So first of all, be careful about the free body diagrams, especially the second and third one, because we are using pseudo force concept. And then also pay attention to the equation solving. I'm coming to the last part, but yeah. So for example, if I want to solve for A, I will just eliminate A prime here. So from these two equations, from this and this, I will equate the value of A prime. From the first one, it is 10 minus A by 5. Okay. And from the second one, it is 50 minus 7a by 6. Okay, so this will give me 60 minus 6a is equal to 250 minus 35a. So finally I'll get 29a, that is 35 minus 6, is equal to 250 minus 60, so that is 90. Sorry, 190. So I'll get A as 190 by 29. Then I'll substitute that here. So I'll get A prime as 20 by 29. So one more step is remaining, because we have to find the accelerations of M2 and M3 in the ground frame. So I'm coming to that, but we're almost there. Okay, now the final thing to find the individual accelerations of M2 and M3. So you need to come back to this picture and understand that, see, these accelerations that we had written, A prime, they are with respect to the pulley P2. And the pulley P2 itself is coming down with an acceleration of A. Okay. So let's just magnify this diagram first. Okay. So we'll understand here that, okay, so this means that with respect to ground frame, what is happening? With respect to ground frame, okay, M1 has an acceleration of A upwards. So that is what we had calculated over there, 190 by 29 meters per second square upwards. But M2 in the ground frame, what kind of acceleration it will have? See, with respect to this pulley which is coming down at A, it is having an acceleration of A prime upwards. Okay, so in the ground frame, M2 is also having an acceleration A2, which will be downwards, but equal to how much? A minus A prime downwards. So that will be 190 by 29 minus 20 by 29, or 170 by 29 meters per second square downwards. Whereas M3, it is going down at A prime with respect to this pulley, which is already going down at A. So it will have an acceleration of A plus A prime downwards. So 190 by 29 plus 20 by 29, or 210 by 29 downwards in meters per second. So these three are the accelerations of the blocks with respect to the ground frame. This one is going at this much upwards, this one is coming this much downwards, and this one is coming this much downwards. Okay, so that is why I told you that this question is a little bit complicated. Okay, so please make sure you go through this and understand the solution carefully. Okay, now let us come to question 31, and particularly we'll focus on the C part of the question also, part C. Okay, so hope this question is fully clear. Now let's move on to the 31st question. So 31st is an example where we'll make use of constraint relation concept. The main thing that will be important for us to understand here is the relationship between the acceleration of this block and the acceleration of the other block which is hanging vertically. There's a pulley attached here, and the other end of the string is like this, hanging vertically, but this end of the string is going around this pulley and then attached to the clamp of the second pulley. Okay. So the first pulley is attached, or you can say clamped, to this block. This is pulley P1. Second pulley is clamped to the corner, but also the thread that is going around the first pulley is coming back here and it's attached to the clamp of the second pulley like this. Okay. So this point is a fixed point over here where the thread is attached. Okay. And of course, we have this block here of mass 2m. So let's say this is block A, and we have this block here of mass m. Let us say this is block P. Okay. So a couple of things important over here. Uniform amount of tension acting everywhere. Okay. Because it's a massless thread after all. Okay. And because the string is going around like this over here, very important that if this has an acceleration of A, what about this one's acceleration? This will become how much? It will become 2A. That you can see from the thread length conservation. If the block E moves by a distance x, it will release how much thread? 2x. So B will get pulled down by 2x. Okay. So when E moves by x horizontally, it releases 2x thread length. Okay. So B moves down by y equal to 2x. Okay. So therefore, the downward displacement is to the horizontal displacement relation is 2:1. That's why acceleration of B is to acceleration of, sorry, my mistake. If this one is A, then this one will be 2A. Right. So if this moves by x, it will release 2x amount of thread. So y is equal to 2x. So y is double of x. So acceleration of B will also be double of acceleration of E. So this is the constraint relation I was telling you about. Okay. So this needs to be taken into account when you are solving this. Okay. So now just make the free body diagrams and solve for these accelerations. Right. So let us look at the substitution of the equations. Okay. So for the block B, you can see that you have mg minus t is equal to mass into acceleration, which is 2a. Okay. Whereas for the block A, you have the weight is getting balanced by normal reaction, so you don't have to worry about that. But this 2t is acting horizontally on E. This 2t acting like this, which is giving it an acceleration of E. But remember, mass of A is 2m. So 2t is equal to 2m into E. So now you have to just solve this very easily. So substitute from equation 2, you have T is equal to ma. Substitute that in equation 1. So you have mg minus ma is equal to 2ma. So you're getting A as g by 3. Okay. So accordingly, acceleration of A will be g by 3 in this sort of direction, and acceleration of B will be 2g by 3 vertically downwards. Okay, now I'm particularly interested in the third part of the question. Okay, third part of the question is asking you, of course, first let's find the, so this was the A part. B part was to find tension. So tension you can see is going to be MA. So M was given to us or not? So whatever. So we'll just write it as mg by 3. Okay, so that's done. Okay. Now third part, we have to find the reaction force by the clamp. Okay, we have to find the force exerted by the clamp on this the pulley P2. On that particular pulley P2 that you're seeing, which is attached at the corner, you have to find what is the reaction force or the net force applied by the clamp on the pulley. Okay, so how we'll understand that? So for that, you have to understand the free body diagram of this pulley, and it's a massless pulley, remember. Okay. So I'm doing it here. The free body diagram of pulley P2. Okay. So उस पे क्या क्या forces लग रहे हैं? Only this tension and this tension. Okay, this tension below is not acting because that's acting on the clamp. It's not acting on the pulley. The pulley is just this cylinder or just this disc. ठीक है, तो अभी ये दोनों फोर्स उसको ऐसे अंदर की तरफ पुश कर रहे हैं. So there will be some kind of reaction force. Okay, so R is the reaction force applied by the clamp on the pulley. Yeah, if you take G as 10, you can take it as 10 at 10 m by 3. That's correct. So now you can see these two tensions are perpendicular to each other. So in a proper vector diagram, they are perpendicular to each other and they are, so R is balancing them. So R should be equal and opposite to the vector sum of these two tensions. So what will R come out to be here? It will come out to be T root 2, and it will act along this bisector. So it will act along the 45-degree angle like this. So R will be mg root 2 by 3. and acting at 45 degrees to the horizontal. So hope this last part is clear. So if you finish this, we will come to question number 34 next. Question 34 part B. So if you finish writing this down or working it out, please move on to question 34 part B. Question 33 is also a good problem, but we have discussed it in last lecture. Okay. In the eighth lecture of Newton's laws of motion. If you go through my notes, you will see we have discussed that question. So in case that question is confusing you again, you can just revise the solution I had given. Okay, so 34th B part, let's go through it quickly. It has exactly the similar kind of constraint relation which we'll be using, because again it has a system of pulleys. So for the system of pulleys, when we work out the ratio of accelerations, it will come out to be the same. This seems like there is a lot of extra things in it to confuse you, but actually the problem is simple. You see, this is attached to a fixed ceiling. Okay. That's why it's not going to make much of a difference, because this thread length from here to here is a fixed thread length, no? From this pulley to this ceiling, I mean this wall, this is fixed. What is changing is the part of the thread length which is hanging vertically, and also the part of the thread length which is attached between this block and this pulley. Okay. So this M1 here is 2 kg, and this mass here is 5 kg. Okay, so now the important thing is, again, see, this thread length is constant. This part, it's not changing with it. But if this block goes down from here to here, if this goes down by a distance x, how much thread length it will pull? It will pull 2x amount of thread length. So naturally, this block will have to get pulled by 2x. So once again, if this has a downward acceleration of a, this will have to have this time a horizontal acceleration of 2a. And uniform tension T acting everywhere. Okay. So for the block M2, there is tension 2T acting upwards and acceleration A horizontal downwards. Whereas for the block M1, there is tension T acting horizontally and has an acceleration of 2A. Okay, so the equations are then like this. M2G minus 2T is equal to M2A, and T is equal to M1 into 2A. Second equation, and now you solve for acceleration. Given that M1 is equal to 2 kgs and M2 is equal to 5 kg. Okay, so hope the constraint relation is clear to you. Just work this out. Acha, the 32nd question you still haven't solved. Okay. 32nd question, same type of situation like this one only. देखो उसमें क्या हो रहा है? In 32nd question, this is like this, no? So if this block goes down by a certain distance, how much thread it will pull? It will pull 2x amount of thread. So this will move by 2x. Okay. So again, your constraint relation is that this one will have an upward acceleration of 2a if this has a downward acceleration of a. Okay. And tension acting like this. Okay. mg sine 30 acting like this. mg cos 30 acting like this. Normal reaction, right? And on this 2t, its weight, which is 2mg. Okay. Now just solve the equations. So 2mg minus 2t is equal to 2m, the mass of that block, into the downward acceleration. This is for the vertical block, and for this one, T minus mg sine 30 is equal to m into 2a. So you have to solve these two equations. Okay, good. Yeah, Itanju, which part of board you are not able to see? The 32nd question, sorry, the 34th B part is just in this. Just this part and these equations. Got it now? Okay, people, so we will conclude today's session here. Next time we will be starting with friction. Okay, so complete the problems of H.C. Verma. The ones we haven't discussed today in class are easy ones. You should be able to solve them yourself. So go through, acha, no problems. So go through the questions we've discussed in class and then try out the remaining questions yourself. You should not have difficulty. You can also read up a little bit about friction before the next lecture. Either read from the H.C. Verma friction chapter or from your IITians Hub module, and we'll pick that up in the next week. Okay, okay, Danshu, I understood. Thanks. Friction will be starting, Ayush, in the next lecture. Next week's first lecture, we will start with friction. Okay, so that's it for today, people. Wish you all the best.